All right, hello, let's practice our alternating series. Okay, we're going to work through BC Homework 11.3. We're going to start by writing out the first four terms of the series, and then we're going to determine if it converges or diverges, I assume, using the alternating series test. Okay, so starting with n equals 0, okay, negative 1 to the 0 is 1, divided by 1 factorial is 1. Okay, when n equals 1, that'll be the second term, I'll have a negative 1 over 2 factorial is 2 times 1. Okay, then it'll become a plus 1 over 3 factorial is 6, and then minus 1 over 4 factorial is 24. I might put a dot, 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 because I know it's going to keep going, right? Because it's going to add all the way up to infinity. All right, and I'm going to say, all right, these terms are alternating. They are decreasing in absolute value, right? Because really n plus 1 is growing, and this is not. And their limit is 0. These terms are going to get as small as you want them to get. So it's going to converge by the alternating series test. Okay. With these conditions together, that gives you convergence by the alternating series test. All right. 3 to the 2n over 10 to the n plus 1, this is not an alternating series. Okay, well, we'll just write out some terms, see what happens. Okay, 3 to the 0 over 10 to the first. Plus, when n is 1, that's 3 to the 2 over n at 10 to the 2. Just call it 10 to the 2. So it'll just be a lot to write out by the time I get to 4. Okay, when n equals 2, I've got 3 to the 4 is 81 over 10 to the 3. And fourth one would be 3 to the 6. Okay. All this to say, I can see what's happening with this pattern. Each term I'm multiplying on top by 9 and bottom by 10. So this is geometric, pardon me, with r equals 9 divided by 10. Okay, since the absolute value of r is less than 1, I know that means the series converges. I'm going to say it converges absolutely, because I told you that, when it comes to converges absolutely versus conditionally, all the ones that we talked about before that were all positive numbers, well, those just converge absolutely. Okay, 1 over n log n. All right, this one, it's not a p-series. We're not going to be able to limit compare with, can we limit compare? I don't think you can. You can't limit compare with 1 over n. Yeah, we don't have that limit's not determined. You need a lot more tricks in your limit tool bag. Can't do direct comparison against the harmonic because the harmonic series diverges, and the thing isn't. I think it's smaller than the terms of the harmonic series, so that doesn't tell you anything. We got to use the integral test, okay? And I'm going to need a thinner pen. Okay, so we're going to run the integral from 2 to infinity over 1 over x log x. If you don't see that as a possible use substitution, what you should do is write it as 1 over log x times 1 over x dx, right? Okay, because the derivative of log x is 1 over x, so this will match up perfectly. I'm going to let u equal natural log x so that du is 1 over x dx. I'm going to convert the bounds. Okay, x equals 2, u equals log of 2. At infinity, well, u goes to the log of infinity. Think about what happens to log as x goes to infinity. It's just going to be infinity again. Okay, so this is equal to the integral from log of 2 up to infinity of 1 over u du. Now, you might remember that this isn't going to converge, right? I need more power in this denominator. But we're going to just show that. equals the log of the absolute value of u as u runs from the natural log of 2 up to approaching infinity. And I'm going to, so a little more room, turn this into a limit. Okay, and for the same reason that this stayed infinity, okay, this is going to go infinity as well. So I conclude that the series diverges. Okay, and that one I just had to use the integral test because first of all I had noticed that possible u substitution, and second, nothing else is going to work. Okay, I, in general, try not to use the integral test unless I absolutely have to, and that was a situation where I definitely needed to. Okay, into the -3 divided by e. Okay, we're going to want to write that as a fraction, right? Because we know that all of the good series are fractions. So that's 1 over n to the +3 divided by e power. Okay, this is a p series with p equals 3 divided by e. E is between 2 and 3, so this number is bigger than 1. Okay, so this is converging by p series test. Okay. P is equal to 3 divided by e, which is bigger than 1. Now we're going to determine if the series converges conditionally, converges absolutely, or diverges. Okay. Yeah, we're just going to be looking at this as a p series. Yeah, these are both p series. Or this one, like limit comparison. So I'm going to take the absolute value of the terms and see if that's still going to converge or diverge, and that will tell me, you know, whether it's conditionally convergent, absolutely convergent, or divergent, right? I think neither of these are going to be divergent because they are alternating while being bigger on bottom. Well, we know that in general that's pretty much that's the condition for convergence there. Okay, so if I took the absolute value of the terms, let's consider 1 to infinity 1 over n plus 1 squared. Okay, I know that this one's going to converge by limit comparison against 1 over n squared. Okay, but we're going to practice justifying our answers. Okay, because otherwise you could be like, all right, cover that up with your finger. 1 over n plus 1 squared. We know that converges. So if it converges even when you took the absolute value of the terms, it's going to converge absolutely. Okay, so I know this one's going to be converged absolutely, but okay, so let's just, think about this one for a second. Okay, I know that the sum of 1 over n squared converges by the p-series test with p, which is 2 being bigger than 1. Okay, then I'm going to do the limit comparison. Okay, the limit of the ratio of these terms to those terms, well, that's going to be 1. Okay, and that ratio is positive and finite. Okay, so as a result, I'm saying that this one converges. Okay, and so I'm going to now say that since the sum of the absolute value of the terms converged, I conclude that the original series converges absolutely. All right. Now this one. Okay, this one will be a little easier because when I strip the alternating part out of it, I'll be left with a p-series, and it won't be too hard to show that it's going to be converging. I won't have to go through the whole rigmarole for limit comparison. Okay, so we're going to go over here. We're going to say, all right, let's just look at let's look at the series that's related but not alternating. 1 over n times, I gotta assume that's a cube root of n. I really can't read it. I think. So we're just going to call that n to the 4/3. This one converges by the p-series test. Right? P is equal to 4/3, which is bigger than 1. Okay, now I'm going to say that since the sum from 1 to infinity of the absolute value of the terms converged, I could say converges or converged, whatever you want. The series that we're interested in, this one converges absolutely. All right, here I've got some more. This is same on top and bottom, so I know that it's not going to be converging. I'm going to say that I'm going to try to use the divergence test here. I'm going to say the limit as n approaches infinity. I'm going to maybe factor out the cosine pi n into the front, multiplied by n over n plus 10. Okay, well, cosine of pi n, that doesn't have a limit as n approaches infinity. It's just going back and forth from -1 to 1, right? And then this is getting closer and closer to 1, so you know, it's, I don't know, it's limit d and e's. All right, and it's certainly not equal to 0. So the series diverges. Okay. This one is bigger on bottom by exactly 1, and it's alternating because it's got the cosine pi n, so that's telling me that it must be conditionally convergent, like the alternating harmonic series. So I would say what's going to happen here is going to be, all right, take out the alternating part. Sum of 1 over n diverges because it's the harmonic series. Okay. We're going to do the limit comparison. Limit as n approaches infinity. And I'm just comparing this to the one where I've taken out the alternating part, right? Because I'm going to say that because it diverged when I took out the alternating part, but it was still, you know, terms were decreasing, alternating, and going towards 0, that's conditional convergent. So limit as n approaches infinity of n squared over n to the 3, n to the 2, and n divided by 1 over n, so it would be times n over 1. That equals 1, and that is positive infinite. And so that means that the sum from 1 to infinity of n squared divided by n to the 3 plus n to the 2 plus n to the 1 also diverges. Okay. Now I'm going to also say that, what's me to say? Oh, so I'm going to say that the series itself definitely converges by the alternating series test because it's bigger on bottom and alternating, but we need to check the 3 conditions. That's they're alternating, they're decreasing, so n squared over n to the 3 plus n to the 2 plus n is decreasing, and their limit is 0, so the limit of cosine pi n multiplied by n to the 2 divided by n. That limit is equal to 0. So since it converges, but if I took the alternating part out, it would not converge, that's conditionally convergent. Okay. And I think I'm going to not be, doing all of the, full-blown justification as if it was a free response question on my AP exam. From here on out, I think that'll be enough. -1 to the n divided by n times 2n. Okay, now this one,
Okay, it's definitely bigger on bottom, right? This is growing and that's staying the same. So the limit of the terms is 0. You know, the bigger n gets, the bigger this thing gets, so the smaller the terms get, and they are alternating, so I got a -1 at the end. Okay, so I just need to, okay, so maybe I'll say first, this one converges by alternating series test. And I'm not going to justify that. Okay. Now I'm going to consider what would happen if it wasn't alternating anymore. 1 over n times 2 to the n is less than 1 over 2 to the n, right? Because as n gets bigger, I'm just multiplying by more in the denominator. I got a smaller fraction. And I know that this is finite because it's a geometric series with ratio between -1 and 1. So that means that 1 over n, 2 to the n converges, which means that -1 to the n over n, 2 to the n converges absolutely. Okay. And this one, because it is bigger on bottom by only half of a power, this is the type of thing that I would do limit comparison against 1 over the square root of n to show that it diverged if it wasn't alternating. It converges by the alternating series test. If I take it out, it diverges. That means it's going to be conditionally convergent. Converges by the alternating series test. That's what happened. That diverges by comparison to the very similar one. Okay, therefore, converges conditionally. All right. This one, the third root of n squared. Okay, it's going to be the same story as this, right? It converges because it's alternating and bigger on bottom, but the power itself isn't, it would be n to the 2/3 power. That's not going to be big enough to converge if it doesn't have the alternating thing. I'm going to put in here, converges conditionally. And if you need more support on that, just come talk to me about it. I'd be happy to talk to you about that. Well, you don't know that this converges. Okay, I'm going to tell you it does. You could say, I guess you could do direct comparison on it against 2 to the n. I think, because past a certain point, n factorial is definitely bigger than 2 to the n. I'm just going to tell you it converges using a test that we'll learn about next class. Okay. And so this converges, therefore, yeah, that series converges absolutely. What do I got back here? I got a bunch more problems, and I think I'm only going to be able to do a couple of more in this sitting, and I'll have to pick this back up a little later. Okay, so let's just do these. All right, determine whether this series is convergent. N to the third over 3 to the n. Yeah, 3 to the n does grow faster. Yeah, I'm going to use the alternating series test. Yes. The terms alternate. And the second bullet point. N to the 3 over 3 to the n is a decreasing function. Okay. And also, the limit as n approaches infinity of negative 1 to the n minus 1 n to the 3 over 3 to the n is equal to 0. Okay. So I'm going to conclude that yes, it does converge. For what values of p is this series conditionally convergent? Okay, well, for comparison, I've got negative 1 to the n over n to the p. That series is conditionally convergent when p is between 0, so p has got to be greater than 0, and I think less than or equal to 1. So if I want this series to be conditionally convergent, p minus 1, because this is like n to the first power, p minus 1 needs to be in that interval. So that would be add 1 to all 3 sides. P is between 1 and 2, including 1, but not including 2. Okay. Which of the following statements is true? Oh, okay. Well, it looks like I used this one on the homework. Okay, I thought I've been using this one on the test. I probably used it on both of them last year, honestly. This is not an option for any series ever. Okay, that's just not a thing that happens. If it converges, it's either converging conditionally or absolutely. Okay, I'm going to say that this one converges conditionally because if I took away the alternating part, the negative 1 to the n, I would be having cube root of 1 over cube root of n. That's a divergent p series. So I'm going to, and, it does converge because it's alternating and, growing faster on bottom. That's really all we need. And so I'm going to say it converges conditionally. All of a sudden, this problem set's moving much faster. Okay, determine whether the statement is true or false. Diverges by the alternating series test. You can't determine. That only tells you if something converges, right? Yeah, we don't. Okay. Converges by the alternating series test. No, I don't think so. I don't see these terms having a limit of 0. I think they're having a limit of, it doesn't exist, or, 4. So, no. Okay. The series, this one converges by the alternating series test. No. It's not alternating. You can't have negative 1 to the n plus 1 and cosine of pi times n. That doesn't make any sense. Because wait a second. Hold on. Are they always opposite? Oh, okay, let's just plug in n equals 1. When n equals 1, I've got negative 1 to the 2 is positive. Cosine of pi is negative. Okay. N equals 2, I got negative here, cosine of 2 pi is positive. Yeah, it's not alternating because it's always negative. Okay, series does not alternate. Okay, then this series converges by the alternating series test. Yes, it's bigger on bottom, it's alternating, yes. Finally. Okay. Which of the statements is true about the sum from 2 to infinity of an, where an is that? Okay, this is not something you're familiar with. Adding 1 to the n in the denominator, negative 1 to the n in the denominator, that doesn't make any sense. So we're going to write out some terms. Starting at n equals 2, negative 1 to the 2 is 1, over the square root of 2 plus 1. Minus, okay, when n equals 3, I'll have 1 over root 3 minus 1, plus 1 over square root of 4 plus 1. Minus 1 over square root 5, minus 1, and so on. Okay, I'm going to say I don't think that these terms are decreasing in absolute value, right? Pretty sure that root 3 minus 1 is bigger than, or is like smaller than root 2 plus 1, and so, this term would be bigger than that term. Okay, so that's just not going to be true. The limit of the terms is definitely 0 because the denominator is growing. Not very fast, but yeah, that is true. And the series is alternating also, so it's going to be 1 and 3 only. Right, I got 2 more pages. I guess I'm going to be able to probably finish this. Okay, identify the properties of this series that guarantee its convergence. We can do that. It's alternating. Its terms are getting smaller. So, -1 to the n plus 1 over, no, pardon me, that we need the absolute value of the term, so we don't care that it's decreasing. 1 over n log n decreasing. And the limit of the terms, so it's -1 to the n plus 1 divided by n log n. That limit is 0. Now, explain why the sum of the series is less than 1/3. All right. Oh, okay, so I'm going to consider the first 2 partial sums. This has to do with the error bound. So 1 over 3 natural log 3, and we're allowed to use a calculator here. So okay, that's 0.303. So S1 equals 0.303. S2 is equal to, as S2, oh, wait, whoops. -1 divided by 4 log 4. That's 0.123. Okay. We know that S is between S2 and S1, because if you have consecutive terms of a convergent alternating series, consecutive terms form like a boundary, because we know that it's going to converge down onto some number that's between, because the terms are getting smaller and they're alternating, it's going to bounce back and forth. But the distance is bouncing back and distance is bouncing forth is decreasing. Okay, so I know that any 2 consecutive ones have the thing trapped in there. S1 is less than 1/3. Therefore, S is less than 1/3. Okay. The infinite series is approximated by Sk, the partial sum formed by adding the first k terms of S. What is the lowest number of terms required to approximate S with error less than 3/100ths? Well, I know that error is less than 3 over 100. Error is also no more than the absolute value of the next term. Okay. So okay, so we're saying, okay, these terms are 2 over n, right? So the absolute value is 2 over n. So that 2 over n goes less than 3 over 100. So, I don't know, we're definitely going to be having a positive n. I guess it should be k. It's not too late. Okay, and I guess I'll multiply both sides by 3 and divide both sides by 100. Wait a second. Yeah, let's flip the fraction, which is going to reverse the direction of the inequality. Okay, so k needs to be greater than 66.667. Okay, once you solve that. And so if k is bigger than that, then it's tough when it comes back not a whole number. I'm just thinking about it. Okay, so suppose we use 66 terms. Okay, the error in that approximation would be less than or equal to the absolute value of term 67, right? And that is 2 divided by 67 is 0.029. Yeah, that's less than 3 over 100. Okay, so that's going to be the answer. Okay, usually I try to do it, like get the answer, get it wrong one time. I was thinking about it wrong. Let's use 65 terms. error is less than or equal to 2/66, and I know that's less than 3/100. I don't think that 2/66 is going to be less. Right, yeah, it's still bigger than 3/100. So, okay, there's that. And then I think, you know what, I'm going to do these last two for this sitting, and then I'll come back with problems 21 through 23 in a separate video, I guess. Approximate the value of f of 1/2 using the first 4 terms of the series for f. Okay, starting with n equals 1. -1 to the 2 is +1, divided by 2n plus 1 factorial. Okay, so that's 2 and 1 is 3 factorial, times 1/2 to the 2. It's going to alternate, so I'm not going to worry about that anymore. When n is 2, that's going to be 5 factorial. X to the 2n would be 1/2 to the 4th. Okay, 1/7 factorial. And this is where n equals 3, x to the 6. Because x is 1/2. I'm plugging in 1/2 for x right there. Okay, that's 1, 2, 3, 4 terms. Now we're just following the pattern, right? We've got 4 terms. That's some bad number. That's probably really close to the true value. Okay, so the error is less than or equal to the absolute value of the next term. Okay, the next term is going to be, I'm going to have 11 factorial and 1/2 to the 10th. So 1/11 factorial times 2 to the 10 is, I mean, like, it's really, really small. Let's see. Where is it? Yeah, there it is. Whoops. Forgot to give it a numerator. And see, it's, yeah, 2.4 times 10 to the -11. And that's just like a really, really, really small number. Okay, that's basically 0. Okay. And yeah, that's going to be all for this video. I'm going to come back a different time and record the solutions for the last few problems. But this has been a good selection of practice problems, so thanks for watching.